Hello. Hello.
Hello.
Hello. Good morning.
Morning. Good morning, sir.
Sir, good morning.
Morning. Hi. এনেইটো 11:30 পৰা হোৱাৰ কথা আছে।
Hi, sir. Yes, sir.
আচ্ছা অলপ টেষ্ট কৰিব পাৰিম নেকি?
Permit. Sir,
ৰ'ব মই হেৰি স্ক্ৰীনখন হেৰি কৰিছোঁ। Maybe the host can share this meeting. Okay. Minimize. কি হ'ল? Hello.
Hello.
এইটো দেখোন হেৰি আহি আছে only the host can share in the meeting বুলি লিখা আছে।
Sir, এতিয়া চাওকচোন।
আহিছে দিয়া। হয়। এক মিনিট মই চাই আছো দেই। Start কৰোঁ। আহিছে নেকি?
আহিছে, sir.
আহিছে?
আহিছে।
ৰ'ব মই আৰু বেলেগ এখন স্ক্ৰীনত যাম এতিয়া তেতিয়া আহিছে নাই কওঁ। এতিয়া আহিছে?
আহিছে।
এতিয়া?
আহিছে, sir.
বেলেগ এখন আহিছে?
আহিছে। বেলেগ আহিছে।
ঠিকে আছে আজি তেতিয়া ঠিকে আছে কিন্তু ভিডিঅ' অহা নাই চাগে?
ভিডিঅ' অহা নাই।
ছাৰৰ মানে
ভিডিঅ'টো নাহি ঠিক আছে বাৰু ভিডিঅ'টো নাহিব মোৰ এনেই আহিব কিন্তু মানে শ্বেয়াৰিং কৰিলে নাহে। ৰ'ব মই আৰু এটা বস্তু চাম হা এক মিনিট ৰ'ব 24 আহিছে নে এতিয়া?
আহি আছে।
আহি আছে ন?
হয় স্যার।
এক মিনিট এতিয়া আহিছে?
স্যার আহিছে।
আহিছে ন?
হয় স্যার।
আচ্ছা ঠিক আছে এক মিনিট ৰ'ব 24 মিলা নাই দেখোন আৰে 7 কিবা এটা মিলা নাই এক মিনিট ঠিক আছে মই এইটো ঠিক কৰি ল'ম এইটো ঠিকে আছে এতিয়া ভিডিঅ'টো আহিছে নে কো
আহিলে স্যার।
ভিডিঅ' আহিছে ন?
আহিছে স্যার।
ঠিক আছে ঠিকে আছে হেল্ল' হেল্ল'
Sir. Oh,
মই হেৰি পিন
Sir.
কৰিব পৰা নাই পিন কৰিব পাৰে যে এইটো হোৱা নাই দেখোন মানে ভিডিঅ'টো অফ কৰিব পৰা নাই মই
আচ্ছা আচ্ছা Sir, ওপৰত এটা ৰঙা হেৰি এটা থাকিব ভিডিঅ' বুলি ষ্টাৰ্ট ভিডিঅ' এনেকুৱা এটা থাকিব
নাই সেইটো
ক'ৰবাত
নাই
start video মিউটৰ
এতিয়া
কাষত থাকে স্যাৰ
এতিয়া
মিউটৰ
এতিয়া আহিছে চাগে
হৈ গ'ল
এতিয়া আহিছে এতিয়া অহা নাই আচ্ছা ঠিক
এতিয়া
আছে
অহা নাই
হ'ব
স্যাৰ এতিয়া নামটো
হ'ব
আহি আছে
মই অলপ পিছত আকৌ আহিম তাৰমানে এতিয়া মই কিবা এটা ঠিক
ঠিক
কৰি
আছে
লওঁ ঠিক আছে
ঠিক আছে
অ'কে
ঠিক আছে
অ'কে Hello.
Sir.
হয় মই আহিলো ঠিক আছে মই ৰেডি আছো আপোনালোকৰ হলে কৈ দিব
So can we start?
Yeah.
So Principal sir. Sir, Principal sir, can we start? Good morning to you all. I am Dr. Korobi Devi, Assistant Professor of Department of Mathematics and Statistics, Golaghat Commerce College, and coordinator of this webinar. On behalf of the organizing committee and college fraternity, I welcome you all to the national webinar on the story and history of pi, a mathematical constant, organized by Department of Mathematics and Statistics, Golaghat Commerce College, in association with Internal Quality Assurance Cell of this college. We have with us respected principal of the college, Mr. Paresh Soike sir. I would like to request our respected principal sir to inaugurate the webinar with his inaugural speech. Over to you, sir.
Thank you, Korobi. Good morning to you all. Respected Professor Noyendip Deka Borua, Department of Mathematical Science, Tezpur University, Dr. Jibanjyoti Kakote, Coordinator of I2AC, Golaghat Commerce College, faculty members of Department of Mathematics and Statistics, Golaghat Commerce College, members of the webinar organizing committee, and my dear participant friends. I welcome you all to this national webinar on the story and history of pi, a mathematical constant organized by Department of Mathematics and Statistics, Golaghat Commerce College in association with IQAC. The number pi is a mathematical constant. It is defined as a ratio of a circle's circumference to the diameter, and it also has various equivalent definitions. It appears in many formulae in all areas of mathematics and physics. It is approximately equal to 3.14159. Being an irrational number, pi cannot be expressed as a common fraction, although fractions such as 22/7 are commonly used to approximate it. Its decimal representation never ends and never settles into a permanently repeating pattern. Because of its most elementary definition relates to the circle, pi is found in many formulae in trigonometry and geometry, especially those concerning circles, ellipses, and spheres. Several books devoted to pi have been published. Also, record-setting calculations of the digits of pi often results in news headlines. To know more about such a widely used unique number, Department of Mathematics and Statistics, Golaghat Commerce College is organizing this national webinar, inviting a prominent resource person. I am very hopeful that the webinar is going to be very lively and our participants would be highly benefited from the session. With these few words, I declare that this national webinar open. Thank you.
Thank you, sir. We have with us respected coordinator of Internal Quality Assurance Cell of Golaghat Commerce College and head of English Department, Dr. Jibanjyoti Kakoti, sir. I would like to request Kakoti, sir, to deliver the welcome address. Over to you, sir.
Good morning to you all. Good morning to you all. Respected principal, sir. Esteemed resource person for today's national webinar, Professor Noyandip Dekaborua. Coordinator Dr. Korobi Devi. Assistant Coordinator Mrs. Tulumoni Gogoi. Members of the webinar organizing committee, the technical support team, and my dear participant friends. I deem it a privilege to welcome all of you to this national webinar on the story and history of pi, a mathematical constant. Organized by the Department of Mathematics and Statistics, Golaghat Commerce College, in association with IQAC, Golaghat Commerce College. Nobel laureate Bernard Shaw once said that all literary men had a dislike for mathematics because school teachers never explained to them the significance and application of the subject in real life. I can tell you from my own experience that sometimes some teachers make mathematics more difficult for learners than what it actually is. There is a YouTube channel called Dear Sir, which is very much popular among the school boys and girls. My younger son, who had an apathy towards mathematics, somehow came across this channel, and gradually he has developed some interest in the subject. When out of curiosity, I watched the channel, I discovered a completely different world of mathematics. Many of my doubts, which I had from my school days, got cleared one by one. Even pi, about which I could not make any head and tail in my school days, became dear to me. The title of today's national webinar is so attractive that my son, who is in class 8, has registered for the webinar. What I could make out is that the reason behind his enthusiasm is the presence of the two words, story and history, in the title. If the title were simply pi, a mathematical constant, he would certainly have not registered for it. What I mean to say is that unless mathematics can be made as attractive as storytelling, particularly in schools, more and more students will continue to find it dull and difficult. I am sure today's webinar would be as interesting as listening to an interactive story, as the title rightly indicates, and the participants would begin to love pi. I once again welcome you all to this webinar. Thank you very much.
Thank you, sir. Most probably, pi is the first Greek letter that all of us are first familiar with during our school days, while calculating circumference of a circle. After that, in almost everywhere in mathematics, we find the rule of pi. Not only in mathematics, pi has been widely used in physics, statistics, and in sciences. So the theme of today's webinar is taken on the Greek letter pi to know more about the role of pi. We feel honored to have Professor Noyandip Dekaborua sir as resource person for today's webinar. Let me give a brief introduction of our eminent resource person. Professor Nayandip Dekaburwa sir is presently the professor in Department of Mathematical Sciences, Tezpur University. He completed his master degree from IIT Kanpur and PhD from Tezpur University. His specialization is number theory, Ramanujan's mathematics. He has got a large number of publications in both national and international journals, including International Journal of Number Theory, the Ramanujan Journal, Discrete Mathematics, etc. Thank you, sir, to be the part of today's webinar. Now, I request our research person, Professor Nayandip Dekaburwa, sir, to deliver his lecture. Over to you, sir.
Okay, so thank you.
So your mic is muted.
Hello. Hello.
Sir, it's audible. Yes, sir.
Audible. Okay. So thank you very much for the kind introduction, and I'm quite grateful to the organizing team for inviting me to interact with you. So I'll be talking about pi, some history and some story about it. And so I'm going to share my these slides, but during that period, my video will be off, unfortunately, due to a technical reason. Okay, yeah, so if you have any problem or if my voice breaks, then kindly let me know. The moderator, kindly let me know. Okay. So is it visible? Is my slide visible? Yes?
Yes, sir, it is visible, sir.
Okay, so that is the title of my talk, the story and history of pi. So that we all know a mathematical constant, and the principal sir has already told that it has many applications in other branches of science. And not only that, the symbol pi, it immediately recognizable by the public also. And from our school days, we know that 22/7 is an approximation of the value of pi. But pi is irrational, and 22/7 is rational. So 22/7 is just a rational approximation. So, but it is a very nice and interesting history. This has been studied for a long time, over 4,000 years. That means over 4 millennia, this constant has been studied. So therefore, it is also known as the constant of the king of constants. That means this is recognizable by everybody, and it appears in almost every branches of science, in physics, in chemistry, everywhere, in engineering. Okay. So since it is recognizable by the common people and public, so it is in our culture, it is in our movie. For example, the movie, the Life of Pi. So there is pi is mentioned, and there is a Pi Day, which we observed on the March 14. Okay, so I'll be talking about all these things briefly. And then it is interesting to know that though the pi has been studied for over 4,000 years, but there are only 5 or 6 actual methods of calculating the value of pi. There are many other formulas, but mainly 4 methods are there. And and many of the great mathematicians of ancient time and modern time are involved in the study of pi. For example, long back, the Greeks, then Archimedes, Euler, Gauss, then Ramanujan, and many more are involved in this study of pi. And this is the only constant that has been studied quite extensively till today. Okay. because the last paper on the pi that appeared just in last 18th of July. So that is a very good paper. So I'll mention that. So some of the mathematics part will be difficult to follow by school students, but they can ignore that. But I think that they will understand the flow of the talk. Okay, so first I will start with Pi Day. Because of the popularity of Pi, there is a day, special day that is called Pi Day. So I'll be talking about Pi Day now. So you see that March 14 is a Pi Day. March 14 is a Pi Day. Why? Because March 14 is written as 3/14. That means 3/14 in Western countries. And the value of pi, approximate value of pi to 2 decimal places is 3.14. So therefore it resembles with March 14. So therefore March 14 is being observed as Pi Day. And because of popularity of Pi Day, the UNESCO decided in 2019 that March 14 would be celebrated all over the world as International Day of Mathematics. So therefore, from this onwards, that means 2020, we are celebrating Pi Day as International Day of Mathematics because it attracts the common students, mathematics students, science students, and the general public. And that gives the very good impetus to the mathematics and science. So therefore, March 14 is observed as Pi Day. And the celebration of Pi Day was actually started at San Francisco's Exploratorium in 1988 by Larry Shaw. Okay, so Larry Shaw was the curator of that exploratorium, science exploratorium. So in 1988, this is Larry Shaw. So he observed the Pi Day with his colleagues. So you can see that there is a procession of pi digits, 3.141, etc. So Larry started Pi Day in 1988. And I'm delighted to now they say that the Pi Day in Assam started in 2008 in Tezpur University. So possibly for the first time in Assam and maybe in India, because I do not know the other the news or records at that time. So in 2008 we started celebrating the Pi Day in Tezpur University. So I have some these posters for that. This is a page of the flyer is here. So this is our flyer in 2008 that we observed Pi Day. And we had some competitions, the Pi Day cake, then Pi Day song, Pi Day procession, etc. Okay. So, and we had a competition of recitation of pi digits from memory. Okay. So we had that, and there is a local pie eating competition and pi symbol making competition, etc. So this was our first Pi Day cake in 2008. So we cut the Pi Day cake, and we actually sung this Pi Day song. So happy Pi Day to you, happy Pi Day to you, happy Pi Day to you all, happy Pi Day to you. Okay, so you can see that it is very interesting that to celebrate a mathematical constant like this, like a birthday. And interestingly, this 14th March is also the birthday of the great Einstein, and as well as the great mathematician Wacław Sierpiński of Poland. So we had also pi exhibition. So this is the pi exhibition on our wall. All pi formulas were written there, over there, and students just had a glimpse of this. So, and we had a Pi Day procession in the campus. So in 2008, so we had the Pi Day procession taking all pi symbols and other formulas. The students took out a procession, and we assembled at the end in the university gate. This is the old get-up of our Tezpur University gate. And we had pi recitation. So the student, he was integrated MSc student, he was reciting. He was citing higher secondary student, Mr. Manzil Saikia, Dr. Manzil Saikia. So he was our integrated MSc student. Then he did his PhD, and now here he is in Cardiff, University of Cardiff, doing postdoctorate. So, and he is the founder of the well-known Ganit Sora. Okay. Another student reciting the value of pi, and another student, school student. And we had pi symbol making competition. So this is, you see that this is fruit pie. So this pi symbol is made up of all fruits. Then we had flower pie. So the students made the flower pie, and that is the abstract pie, some abstract drawing were there. Then this is salad pie. This is interesting. This pie symbol is all salad. This is cucumber, tomato, then other things. Okay. And we had this heart pie. Then we had this dal pie. That means all masur dal and mung dal, etc. All these dals. Okay. So an innovative way of making pie were made by all university, college, and school students. So it was a grand success. So another school students. And we had pie eating competition, because in Western countries, our actually pie symbol pi is pi, but PIE, that is American pie. So in actually USA, they celebrate Pie Day by eating pie, American pies. So we had also some this one, pie eating competition. So one has to eat these pies without using hands, only they can use mouth. So, and we continued the following year as well in 2009. This is the Pie Day cake, beautifully made by one local restaurant. So this is, you see that Happy Pie Day is written here, and 3.14159 is written here. So that is celebrated in 2009. And I'm very happy that people in Assam, in different places, they have started celebrating this Pie Day. Okay. And winners of pie eating competition in 2009, they are the winners, proud winners. And this is the winner of pie symbol making competition in 2009. So you see that this is a pie. This is a pie. One student is up, and he cannot go up like that. So therefore, there was another fourth student, and all four are here. And interestingly, all are from BTech department. Okay. Now they are well placed. So this is very popular. I want to just give one example how popular it is. So you see that in 2018 in Sultan School, Muscat, so they made the longest human representation of pi digits, 1,182. So they made 3.14159 by taking placards. They made this pi, this spiral. So more than 1,000 people were there. Then in the next year, that means last year, 2019, they made another largest human pi symbol having 1,170 people. All these are those people. Okay, so this is very popular. So, and the Pi Day has been transformed into what? International Day of Mathematics from 2020. Okay. Then why pi? Because I already told you that this has been studied for a long time, over 4,000 years. And the ancient Babylonians and Egyptians, they estimated the value of pi. So you see that there are some clay and stone tablets. This is clay and stone tablets found in ancient Babylon and Babylon. And there are some, in their notation, some formulae are written, and one can infer that the value of pi can be calculated by using those geometrical constructions. And they estimated it as 3, and they did like this. Okay. So then in pyramid, in ancient Egypt, the pyramid, this is called a Rin papyrus. This papyrus was found in pyramid, and there are some mathematical formulae were written. And those from there also, pi can be calculated up to this very 1 or 2 decimal places. And in Bible also, this pi is mentioned. So you can see these bars that also he made a molten sea of 10 cubits from brim to brim. Brim to brim means brim to brim. And a line of 30 cubits did compass it roundabout. So this round is what? 30 cubits. So 30 divided by 10. So circumference divided by 10, and that is nothing but what? That is equal to 3. So therefore in Bible also pi has been approximated as 3. Okay. And in fact, I did not tell you what is pi, but that is already known, I suppose, because if you take any circle and there is diameter, then the ratio C by D, this circumference divided by diameter. And if you take a small circle, then also the circumference divided by diameter, C1, D1, say, those are always same. Okay, whatever big circle or smaller circle you take, the circumference divided by diameter, that is a constant. And that is this is pi. Okay, So here also you see that 30 divided by 10. So in Bible, pi is approximated as 3, but 3 is not the correct one. But anyway, they have tried to approximate. And some of the scholars of Bible, they say that actually this is the perimeter is not circular, somewhat different. Therefore, they got 3. Okay. So, and in India, many mathematicians tried to approximate the value of pi, because when this constant, it was proved that that is a constant, that means circumference divided by diameter is a constant. They wanted to know what type of constant it is. Is it a rational number? It is an irrational number, etc. So they tried to do, but because for rational number, we will always get decimal expansion as finite or recurring. Okay, finite, for example, half equal to 0.5. So it is finite. So here it is finite. But 1/3, this is also a rational number, but your expansion is 0.333, etc. So it is infinite, okay, infinite, but it is recurring. That means 0. This 3 will repeat. Okay, so 1/3 is a rational number, but it is recurring. But pi is not. For an irrational number, the decimal expansion will be always infinite as well as what? Non-recurring. That means it cannot recur. It cannot recur, non-recurring. For example, √2, the expansion of √2, 1. Etc. So this cannot be, this is not recurring. It will go on like this. It will not have a period like this 3. Here there is a period of 3. After 3, it will recur, but here it will not recur. Okay, so therefore they wanted to know whether this pi is irrational or not. So therefore they calculated the value of pi to as many as digits as possible after the decimal point. Okay, so an Aryabhatta, he also calculated pi, and he has given it in his book Aryabhatya in Gulakpad Adhyay. So what he did, so he actually written a shloka. What is the shloka? This is the shloka. Saturadhikanga satam ashtam gunama dvasasthistata sahasranama, etc. etc. Okay. So what is this? Saturadhikanga. Saturadhikanga means Saturadhikam satam. That means 4 plus 100. Then astam gunam into 8. Dvasasthistata sahasranama. That means plus 62,000. This is the perimeter of a circle with diameter what? 20,000. So that is his formula. So this is Aryabhatta's formula. And you see that from here, Aryabhatta's formula, you see that 62,832 you'll get, and 20,000 divided by this. So it is 3.1416. And what is the actual value of pi? The actual value of pi is this one, 3.1415926, etc. Okay, so here. And this is Aryabhatta's value. So you see that it is 3.141. This 3.141 is same as this 3.141. So therefore, Aryabhatta calculated the value of pi at least up to 3 decimal places. Okay. And there are many other Chinese and other mathematicians who calculated the value of pi, like Aryabhatta, Bhaskaracharya, etc. Okay, but the actual mathematical methods, first iterative method was given by Archimedes. Okay, the great Archimedes of Syracuse. Okay, and what he did like this. So he took a circle. So you can see that this is the circle. This is the circle. This is the circle. He took a circle with diameter what? Diameter 1. So circumference divided by diameter. What is this? This is circumference is c, say, and diameter is 1. So length. This c, length of the perimeter, that means circumference is nothing but what? This should be equal to pi, because your diameter is 1 unit length. So therefore, we need to calculate this. What is this? What is this perimeter, circumference? So what he did, he took is hexagon like this, inscribed hexagon like this. And he also took another circumscribed hexagon. Okay, another circumscribed hexagon. Circumscribed means it is outer hexagon. Okay, so outer hexagon like this, outer hexagon like. So therefore, this one, the middle one is the circumference. So that lies between what? The inner hexagon is less than, inner this perimeter is less than the circle's perimeter, and this is outer perimeter, say CO. So therefore pi lies between the perimeter of the inscribed and perimeter of the circumscribed. So starting with inscribed and circumscribed hexagon, he estimated that your pi must lie between 3 and 2√3. Okay, but what he did was that he actually doubled the sides. That means from 6 sides, so he can go up to 12 sides. For example, this is the length of the 6-side polygon. Okay, so what he did, from 6 sides he can calculate 12 sides polygon. This is half. Okay, so not half, twice. So from 6 sides he can go up to 12 sides. From 12 sides he can go up to 24, then 24 to 48, 48 to 96. So going up to 96, so he found that your pi lies between what? 223/71, this one, and 22/7. Okay, and because at that time, by trigonometrical formula, one can easily calculate now the perimeter of those hexagons, but at that time of Archimedes, those were not available. So they have to construct this or use or derive the value by using geometrical constructions only and using the geometry only. So therefore, that was a Herculean task at that time. So after doing doubling 4 times, he arrived at this. But you see that what is 223/71? That is 3.14085, and it is 3.14285. So your pi lies between what? 3.140 and 3.142. So therefore, pi must be 3.14. So therefore, by his method, we immediately get that the value of pi equal to 3.14 approximately. So, but what is the innovative way of Archimedes was that if we can double more and more, we can get more and more values of good approximations of pi. Okay, and that was the method, real iterative method, mathematical iterative method. Okay, so that was quite extensively used by other mathematicians of other countries also, and all the method, all the pi calculations were done on Archimedes method before the advent of calculus. Okay, by Newton and Leibniz. Okay, so and there were some notable infinite formulas, for example, given by Franco Viette, John Wallis, and Lord Brouncker. So this is a very nice infinite product. Okay, so it is square root of half. This is square root of half plus half and square root of 5, and you go on doing that. So that is equal to 2/pi. Similarly, John Wallis, he calculated that pi by 2 is this infinite product, and it is a convergent infinite product. And Lord Brouncker, he has shown that your 2/pi has a continued fraction expansion. This is a continued fraction, 1/1 plus this one, etc. So the fraction is continued in the denominator. So these are called continued fractions. So these are very nice formulas, and you see that they are not related directly to the geometry, as you can see. So these are now related to only numbers. Okay, these are beautiful formulas, but they are not very fast converging. That means these formulas cannot be efficiently used to calculate the value of pi. Okay, so therefore we need some more good formulas or nice formulas which can be used to calculate the value of pi. Okay, and Isaac Newton, he himself calculated 15 digits after discovering the calculus. So you see that this is Newton's formula. So he took an integral from 0 to 1/4, and this integral can be written in terms of this series by his newly discovered binomial theorem. So you can see that this is an infinite series and this is just a finite term. So if I truncate here this infinite series, so you truncate suppose up to say 50 terms, then you will get the value of pi, approximate value of pi. Okay, so that is what Isaac Newton calculated. But this is also a very slowly converging series because Newton himself, so he actually confessed later on that I am ashamed to tell you to how many figures I carried these computations, having no other business at that time. So he was not very happy with his calculations. Okay, then the second method came. Gregory in 1671, he has shown that this integral, definite integral 0 to x, the dt of 1 plus t squared, this is tan inverse of x. And this can be again expanded by binomial theorem and then integrate So we'll see that this is an infinite series. And the beauty of this infinite series is that this converges for mod x is less than 1. So what you take mod x less than 1, any x which is less than 1, then you will get a conversion series for tan inverse of x. And that is what Leibniz did. So Leibniz did x equal to 1 here. Okay, x equal to 1. Then what you get, tan inverse of 1, but we know that tan inverse of 1 or arctan of 1 is pi by 4. So pi by 4 has an infinite series. Okay, so pi by 4 has an infinite series. So you see that though these were discovered in 1671, long back in 1671 and 1674, but in Kerala, Kerala School of Mathematics in India, okay, Madhava, a mathematician of 14th century, 14th and 15th. Okay, he was there up to 15th century. So he developed this type of series. Okay, now we know that actually Madhava derived this type of series. So therefore, almost about 300 years back, he found this series. Okay, so therefore these are now called Gregory Leibniz Madhava series. So therefore, this Indian mathematics was very rich at that time, especially the Kerala School of Mathematics, and the followers of Madhava, Nilakantha Samayuji and other writers, they have written some text on this. Okay, in the following centuries, 15th, 16th centuries. Okay. Is it coming? Hello, I'm checking.
Yes, sir.
Anyone?
Yes, sir.
Is it visible? Okay.
Yes, sir.
Okay, thank you. So that Leibniz, Gregory, and Madhava series were used for different x's. So x equal to 1 is the Leibniz series. Then you can put x equal to 1 over root 3. So that was done by Abraham Sharp. And you see that because tan of pi over 6, tan of 30 degrees is 1 over root 3. So you see that pi over 6 is equal to this infinite series. But this is faster converging series than the Leibniz series because the denominators are very small here. Denominators are large here in comparison to the Leibniz series. So he calculated up to 71 digits by using this variant of that Gregory series. Similarly, John McKean in 1706, he calculated 100 digits by using this famous formula of McKean. And here there are two tan inverse of 1 by 5 and tan inverse of 1 over 239. So one can find the expansion by using Gregory's series, and one can truncate somewhere infinitely and use the value of and use that to find the value of pi. And he did it by calculating 100 digits. Okay. And now an interesting fact happened that William Jones of England used the symbol pi. He used the symbol pi for the first time as it is used today in this book, okay, in his report. And actually, William Jones is not a mathematician. He was just reporting McKean's calculation of 100 decimal places, okay, 100 digits. So this pi was used. Now we use pi, everybody used pi to denote that constant. But only in 1706, this was used for the first time to denote that symbol. So it is a very latecomer in the history of pi. Okay, then in 1761, Johann Lambert proved that pi is irrational. And once this pi is being proved irrational, so therefore one can immediately say that the decimal expansion of pi, that means 3.14159, this will never recur. And this is an infinite non-recurring decimal expansion. So therefore one can calculate up to any decimal places of pi by using sophisticated methods. Okay, but using only McKean type formulas or Gregory type formulas, it is not possible to calculate the value of pi even in supercomputers. So therefore, new methods, new fast converging methods were required. Okay. So then in 1882, Ferdinand Lindemann proved that pi is transcendental. Okay, so we know that root 2 is irrational. Root 2 is irrational, but root 2 is not transcendental. Root 2 is algebraic. There are two irrational numbers, two types, One is algebraic and another is transcendental. And what is algebraic? Algebraic means it is a solution of an algebraic equation. For example, x squared minus 2 equal to 0. So this is the solution of this is nothing but what? One of the solutions is root 2. Okay, so therefore root 2 is algebraic. But pi is not transcendental. Pi is not algebraic. So therefore it is transcendental, and that was proved in 1882 by Ferdinand Lindemann. And what does it mean? This means that pi cannot be solution of any algebraic polynomial. Okay, that means a naught x plus a n xn equal to 0. You cannot get this type of algebraic polynomial as a solution to pi. Okay. All right. So okay. So then in 1844, Viennese Johann Dash, he calculated 205 after making. So 100, then 205 by using this formula. And there are many other formulas actually in this. And the new formulas are used, and so new value of pi were calculated up to decimal places. So I just leave this one. And in 1873, William Jones used up to 707 decimal places by using Mackine's formula. Okay, but that was wrong because D.F. Ferguson in 1945, he used some mechanical calculator to find that actually Shanks' value was wrong at 527th digit. Okay, so it was wrong. So mechanical calculator were invented at that time. So those mechanical calculators were used to find the value of pi, but the formulas are same. That means Mackine type formulas and this Gregory series, Gregory Madav and Leibniz series. Okay. So no new methods were discovered. And so there are many other calculations. So I just checked that. This is in 1946, Ferguson 808. Then Smith and Renz 1120 digits, and all these were done in mechanical calculator. But then our electronic computers came. Okay, so this is the first electronic computer. This is a huge computer. Okay, the first electronic computer, and that is, the name is what? ENIAC, electronic numerical integrator and calculator. Okay, so that is first electronic computer, and that computer was used. This was a huge computer, as you can see. So let me just okay. So you see that ENIAC had what? 70,000 registers, 18,000 vacuum tubes, etc., etc. ENIAC was 10 feet tall. So now you compare the 10 feet tall computer with our small computers. Okay, and it occupied actually 1,800 square feet, and it was weighed 30 tons. So unbelievable. And the ENIAC did only 5,000 editions per second, 5,000 editions per second. But 5,000 editions per second was too fast at that time because in comparison to the mechanical calculators and hand calculators. Okay, so now what happens that new computers came, and new up to new decimal places of pi were calculated. So in 1949, this ENIAC was used to calculate the value of pi up to 2037 digits. Then I just omitted many calculations between, but these are the landmarks that in 10,000 were achieved by Guinness in 1958 in an IBM 704 computers. Then Shanks and Ranks 1 lakh digits in 1961, IBM 7090. Then 1 million by Gilloud and Boyer in CDC 7600 computers in 1973. Okay, so new computers came, and the value has been shoot up. Okay, so 1 million were calculated in 1973, and during that time, one new method were discovered, and that is called arithmetic geometric mean. Okay, we all know what is arithmetic mean. Arithmetic mean of two numbers a and b is a plus b by 2, and what is the geometric mean? Geometric mean is square root of ab. So this arithmetic mean and geometric mean, if you do successively, that means you take arithmetic mean, geometric mean, then arithmetic mean, geometric mean again, of these two numbers, these two numbers, then you will get another arithmetic mean, geometric mean. Then you take these two numbers, you will get another arithmetic mean, geometric mean. But the interesting thing is that these arithmetic mean, geometric mean, these will converge to the same value, and that value is called the arithmetic geometric mean. Okay, so for example, so let me give an example here. So what is the arithmetic geometric mean of root 2 and 1? So you see that this is just 1. You take the arithmetic mean of this and this, you will get this one. Geometric mean, this one. So 1 and 1 are correct. Okay. In the next step, arithmetic mean will be this. So you see that it is all red colored digits, 1.1981 and here 1.1981. They are same. Okay, in the next stage. And you take the next stage again, so you'll see that more than twice digits are correct. 4 digits were correct after the decimal point, but here 9 digits were correct. 9 digits were correct. 9 digits. Then here more than 18 digits were correct, more than twice. So it is more than quadratically convergent. Okay, more than quadratic. The convergent rate is more than quadratic. So it is a very fast converging series, and Gauss actually discovered many properties of this arithmetic geometric mean. Okay, at the very early age of only 14, so Gauss was a prodigy. So you see that he only at the age of 14 he discovered many interesting properties of arithmetic mean and elliptic integrals and perimeter of lemniscate, etc., etc. Okay, and in his diary he also noted down some interesting relations between arithmetic geometric mean and the perimeter of lemniscate, and from there two mathematicians, Salamine and Brandt, in 1976 they discovered the pi formula involving AGM. So this is the AGM formula of Salamine and Brandt, but it was also actually contributed by Gauss. And remember that Gauss actually he was born in 1777 and died in 1855. So in his diary he recorded some formulas, and from those formulas this can be derived, and that was derived by Salamine and Brandt. And this is because the conversion rate is very high, more than quadratic, so this can be used to find the value of pi quite rapidly. Okay, and this is the algorithm for AGM algorithm. So you see that if we use this algorithm, A0, this is the first two values, then you go on taking arithmetic mean and geometric mean. So then your Pn will converge pi quadratically. That means the first iteration will give 1 decimal places correct, then 4 decimal, 9 decimal, 20 decimal, 42 decimal, etc., etc. So it just doubles the digits. So this is a very fast converging series. So all other these Makin type series were not this quadratically convergent series. Those are some formulas which are not quadratic. Infinite series were not quadratic. Okay, so then there are more algorithms were developed by Borin brothers. This is Borin's, not Borin. There are two brothers, Peter and John Borin. So they developed more quadratic algorithms, quartic algorithm, etc. So this is their quartic algorithm. This is quartic means what? Quartic means it 4 times. It quadruples the digits by 4 times. So this is Borin's quartic algorithm. There is nonic algorithm also, then quintic algorithm also, Borin's, but this is the most famous one. This quartic algorithm. This is very usable in computers. Okay, and in 1983, Tamura and Canada of Japan, they calculated the value of pi up to over 16,777,206 decimal places by using AGM algorithm. So, and before that, you see that the 1 million was only 1 million were calculated. Okay, only 1 million were available. The value of pi were available. Okay, so once the AGM algorithm was used, so over 16 million decimal places were found. And then our Ramanujan came to the picture. And I want to mention that all those quartic, quintic, nonic, those algorithms were based on Ramanujan's modular equations. He noted down some modular equations, and from those modular equations, those quadratic, etc., those algorithms can be derived. So Borin brothers did that. And so these are the 3 methods we have got. So main methods, Archimedes, then calculus method, and third one is AGM method. So by using AGM method, more than 16 million decimal places were found. Okay, now our this Ramanujan came into the picture. So I will briefly discuss about Ramanujan's biography. Most of you already know, but let me just briefly discuss because it is very interesting. So Ramanujan was born on December 22nd, 1887 in Erode, Tamil Nadu, in his maternal grandparents' house. Okay. So it was a customary at that time that the first child will be born in the maternal grandparents' home. So therefore he was born in Erode, but Ramanujan's family were actually from Kumbakonam. So after a few months of his birth, they shifted to the original home at Kumbakonam. So this is the picture of Ramanujan's mother, Kumalata Ammal, and there is no picture of his father available. So they moved to Kumbakonam. So his family was economically poor, and this is Ramanujan's home at Kumbakonam, quite a few years back actually. So this one, and now this home has been taken over by Sastra University, and they have converted this into a museum. So if you happens to visit Kumbakonam, then you can see his place. But they have renovated this house, and that is not what the mathematicians are satisfied. That they should not have renovated so much. Okay, and this is another home at Madras, where Ramanujan rented house. This was he was there while in Madras. Okay. Then in 1892, he entered Town High School of Kumbakonam, and as a high school student, he was very brilliant, especially in mathematics. So at the age of 12, Ramanujan borrowed S.L. Loni's Plain Trigonometry and worked all the problems in that book. And the good thing is that this Plain Trigonometry is also available in the market, even in the textbook also we can buy. Okay, so he took this book and he worked out all the problems in that book. But though the name of the book is Plain Trigonometry, but there were other formulas there. For example, calculus was there, infinite series were there, then complex variables were there. So he learned those methods or topics by himself and worked the problems in Loni's book. But one book that changed Ramanujan's this life is at the age of 15, Ramanujan borrowed a book from Kumbakonam College Library, George Subriskar's A Synopsis of Elementary Results in Pure and Applied Mathematics. Okay. And this is a copy, the picture of the book. Hello, am I audible?
Yes, sir, you're audible.
Yes, sir. Yes, sir.
Okay, thank you. So this is the Ramanujan's, he was inspired by this book, George Subriskar's A Synopsis of Elementary Results in Pure and Applied Mathematics. And good thing about Amazon.com is that one can purchase this. So this is my own copy. Okay, so but the interesting thing is Carr was a tutor at Cambridge, and he compiled his book of 4,417 results, mostly without proofs, as an aid in his tutoring. So therefore, he compiled this book for his tutoring only, so for his own sake. The first formula of this book is very simple. So you know this already. Everybody knows A plus B into A minus B. This was the first formula. Okay, but there were many more formulas were there, many more geometrical constructions, infinite series, definite integrals, and so many things were there. So Ramanujan, but no proofs were there. Only thing is that he just went on recording the formulas only, and the proofs were very scanty. That means almost no proofs, and proofs were only hint type. Okay, so therefore Ramanujan himself did all the problems there, and by doing that he learned so many things, and he also discovered so many new results, and he noted down the results in his notebooks. Okay, and in 1904 he entered Government College Kumbakonam, when actually he passed his matriculation examination with a first class and got some scholarship known as Subramaniam Scholarship, Subramaniam Junior Scholarship. So he received that, and he entered there. But by that time, Ramanujan was totally devoted to mathematics. Okay, so he was totally absorbed with mathematics. So at the end of the first year, he failed to pass in the examination and lost his scholarship. And because your family was very poor, so therefore he could not again enter Kumbakonam College. So later on, 2 years later, somehow he entered Pachayappa College in Madras. And once again, he failed his examination because he would not study any other subject except mathematics. And luckily, Ramanujan's last mark sheet is available nowadays. Okay, still available. So let us see how Ramanujan performed. So in English, out of 200 marks, the maximum, minimum required was 70, but he scored only 38. And in Sanskrit, out of 100, he scored 34, and the pass mark is 35, so he narrowly failed. And in mathematics, out of 150, he actually got 85, and minimum required was 45, so here he passed. Okay, and in physiology and history, he did not appear because he was ill, and he was suffering from dysentery and then other problems, so he did not appear. So Ramanujan's formal education ends there. So therefore, because his family was very poor, so Ramanujan was forced to terminate his formal education. So what is Ramanujan's education qualifications? FA failed, FA failed, FA failed. So it is his qualification. So that means higher secondary first year failed, if you want to say in modern language. Okay, but he was not bothered about that. Working in isolation, Ramanujan completely devoted himself to mathematics and continued to record his discoveries in his notebooks. So he recorded his final discoveries in his notebooks because the paper was due to scarcity of papers and other things. So he actually recorded only the final results in his notebooks. And initially he did his, this is 2 pages of Ramanujan's notebooks preserved at Madras University nowadays. Okay, I will come back to the notebooks. Okay, and this is his pose of Ramanujan's home in Kumbakonam. So he, inside there was a cot, and he sat there in the cot and started recording his notebooks, recorded his results in his notebooks. Initially, he did his work in a slate, okay. And usually he used this type of slate to find the results. Okay, and luckily we have this slate is preserved, but that is preserved very privately, and it is not open to public. But I was lucky enough to visit this slate in 2016 in August with Professor Burnt, and this is my favorite picture with the slate. And this is the other side of the slate. And in 1909, Ramanujan married S. Janaki, and Janaki was 9 years old. So without any support or any financial support, Ramanujan actually desperately sought for a job, but he was just FA failed, so only job clerk's position somewhere in government office. So Ramanujan met V. Ramaswamy Iyer. He was the DC, Deputy Collector of Madras Civil Service, and showed him the notebooks and asked him for a clerk's position. And Iyer was also the founder of Indian Mathematical Society in 1907. So Iyer was aware of this some kind of mathematics, and Ramanujan showed the notebooks and for a clerk's position. But Iyer thought that Ramanujan's talent would be wasted in a clerk's position and sent him to R. Ramachandra Rao. He was the collector of Nellore, and R. Ramachandra Rao was also a mathematician. And so R. Ramachandra Rao temporarily given financial assistance to Ramanujan for a few months. But after a few months, Ramanujan declined to take the temporary financial assistance. So with some well-wishers' wish, so Ramanujan was actually appointed as a clerk in the Madras Port Trust office. And in that office, there were 2 very kind men. One was S. Narayana Iyer, and the other was Sir Francis Spring. He was the chairman, and he was the chief accountant, Narayana Iyer. And he was a mathematician. Narayana Iyer was a mathematician. So Ramanujan worked with Narayana Iyer after the office hours, and he was very kind, Narayana Iyer, because his first paper, Ramanujan's first paper, was actually written by Narayana Iyer. So he helped to improve the English of that paper on Bernoulli numbers. So they encouraged Ramanujan to write to British mathematicians. And Ramanujan initially wrote to 3 British mathematicians. He first wrote to M.J.M. Hill. M.J.M. Hill replied, but was not at all encouraging. And because M.J.M. Hill was actually from fluid mechanics, and Ramanujan only sent the formulas, no proofs were given in his letter. So therefore, M.J.M. Hill actually, the reply was not very encouraging. And 2 other mathematicians, Baker and Hobson, they did not reply. And all these 3 were FRS, that means very well-known mathematicians. And there are some good books of these persons still available. Okay. So, and on 16, 1913, Ramanujan wrote to G.H. Hardy. And Hardy recognized that Ramanujan's talent, and he actually, after seeing some of his formulas sent by Ramanujan, Hardy said that they defeated me completely. I had never seen anything in the list like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true. If they were not true, no one would have the imagination to invent them. So therefore, Hardy, by seeing the formulas of Ramanujan's, especially on continued fractions, Ramanujan was a master of continued fractions. Remember that he was FFA, but he knew continued fractions. And he found many new results of continued fractions. Okay, so and Hardy immediately invited Ramanujan to Cambridge to work with him, but Ramanujan was reluctant at the first because he was a Orthodox Brahmin. His family was Orthodox Brahmin, and at that time they thought that if he sailed through sea, then his caste will be lost. So therefore, his mother was opposing and travel to England. But ultimately, after a lot of persuasion from Hardy, so Ramanujan sailed for England on March 17, 1914. And Ramanujan wrote some monumental papers, some of them jointly with Hardy. Okay, and they worked on very prominent, these new areas, some prominent areas, and they discovered many, many new things. Okay. And Ramanujan became Fellow of Royal Society. It was a very highest honor at that time, and now also, and also the first Indian to be elected as Fellow of Trinity College in 1918. Unfortunately, at the end of the 3rd year, that means in about 1917, Ramanujan fell ill, became ill. Ramanujan was a pure vegetarian, and at that time, the First World War was on, and England was a war-ration country, and Ramanujan cooked himself. So he became ill because some of his foods were actually supplied from Madras. So it took months to reach him. So therefore, Ramanujan, and he was busy in doing mathematics. So therefore, there are a lot of things that he became ill. And in the last 2 years in England, he actually was in different sanatoriums, hospitals, etc. And when he partially recovered in 1990, and the war was also almost over, so he returned to India in the hope of complete recovery in March 1919. Unfortunately, on April 26, 1920, Ramanujan died at the age of only 32. So, and actually there are probable diagnoses of Ramanujan's illness. Many people, many physicians at that time actually speculated that Ramanujan might have suffered from tuberculosis, severe vitamin deficiency by not eating properly, then liver cancer and lead poisoning due to not cleaning cooking vessels, because he had no time. He cooked himself. He never ate in the mess. Okay. Hello. But British Dr. D.A.B. Young, he made a careful examination, and he has concluded that actually Ramanujan suffered from hepatic amoebiasis. So in 1994, D.A.B. Young's paper appeared that Ramanujan actually died of hepatic amoebiasis. The illness is difficult to diagnose, but sadly, once diagnosed, it can be readily cured. So it is unfortunate that Ramanujan died at the very early age. And the complete biography of Ramanujan were written by Robert Kennigan. Robert Kennedy, The Man Who Knew Infinity. And one film was made based on these, and Dev Patel was Ramanujan. And I'm not going to see that film because I cannot imagine Dev Patel as Ramanujan. And there are some other novels. Okay. And there are Ramanujan's notebooks. He left 3 notebooks, so I just quickly go through it. So there are 3 notebooks, and all these notebooks were edited by Bruce Barnes of University of Illinois at Urbana-Champaign, USA, and who undertook the task of editing the notebooks in 1977. And he published 5 volumes, 1, 2, 3, 4, 5. Okay. Then, okay, so then I go to this. Okay, now I come to Ramanujan and Pi quickly. Okay, excuse me, can I get some more time, or should I stop?
Yes, sir. Yes, sir.
How much time I can get more?
Yeah, as you wish, sir. 15 minutes.
Okay, okay, I'll be completing. Yeah. So thank you. So now I come to this Ramanujan and Pi. So these are some of his approximations. So you can see that the approximations are not very usual. That means this is like this: 9/5 plus square root of 9/5. So this gives 3.141, and this one you see 3.14159 up to 3. Okay, so these are Ramanujan's approximations, and this actually follows from what is called his class invariance. And the Ramanujan recorded many class invariants, and actually Weber, the German mathematician Weber, he also recorded some class invariants, but Ramanujan recorded 46 new class invariants than Weber. And here he used these to find the value of pi, approximate the value of pi, and other applications were there for class invariants. And all these class invariants, actually, he said that this follows from Ramanujan's modular equations. But that was just his statement. He did not actually mention the proofs. And it took years to prove his class invariance in the spirit of Ramanujan. So he was always sketchy. That means he left something to ponder about his discoveries. And in his famous paper, he recorded those approximations. But apart from those approximations, he also recorded 17 series for 1/pi. Okay, and these series were very peculiar. That means these series were not like ASM formulas or like Makin type formulas, Gregory type formulas. These are completely different. These are series for not pi. These are series for 1/pi. 1/pi. This 4 can be taken here. The 4 can be taken on the right hand side. So these are basically series for 1/pi. So he said that these are from classical theory of elliptic function, and he's just given one hint how he discovered this. Okay, and these series were made famous by one film, Disney film. This is High School Musical. So you see that in the film, the teacher was writing 4/pi. So Ramanujan's formula is also 4/pi. Then the teacher is writing 8/pi, but actually it is not 8/pi, it is 16/pi. So therefore, she is a brilliant student in the class, and she actually corrected that this should be 16. And the teacher is asking, is it? And asking, is it? Then checking, then yes, it is corrected. And that is a good job for the student. So that is the sequence of the film, High School Musical. And after offering those 3 formulas, he said that there are more formulas. Okay, and these are corresponding theories. There are corresponding theories, he said. And what are the corresponding theories? That will follow like this. Okay, and R equal to 3, 4, 6. And what is the classical theory? Classical theory is just R equal to 2. So he derived 3 formulas for R equal to 2, and he said that for alternative theories also there are formulas, and he has given 14 further series for alternative theories, and 2 series for Q3, then 10 series for Q4, and 2 series for Q6. So these are his series, all right, and these are his series. So But Ramanujan never returned to the corresponding theories in his paper, but 6 pages of his second notebook are devoted to developing these theories, and but without any proofs. So these were proved only in 1995. And then Ramanujan series were then forgotten by the mathematical community. And on November 1985, R. William Gospar used one of Ramanujan series, this one, to calculate the value of pi up to what? Over 17 million decimal places. And when these 17 million digits were calculated, the previous record was 16,777 by 2 and 206 decimal places by using ASEM formula. As I already told you, that Canada and his colleagues calculated this by using ASEM formula. So once Gospar calculated the value of pi up to 17 million decimal places, and people were astounded that how, yes, but these were not proved yet. The Ramanujan's formulas were not proved yet, only he stated. Okay, so a comparison of Gospar's calculation of digits of pi with that of Canada and Tamura made it extremely unlikely that Ramanujan's series was incorrect. And at about the same time, 2 brothers, Jonathan Borroin and Peter Borroin, they actually proved all Ramanujan 17 series of in their book Pi and the ASEM. And they also found many more series for 1 over pi. But unfortunately, their methods were not in the spirit of Ramanujan. Not all, but some of those are not in the spirit of Ramanujan. Okay, and they have also published many papers. And at about the same time, another 2 brothers, Sudnovsky brothers, they derived new series representations for 1 over pi, and their method was also quite different. They used complex function theory, complex multiplication theory. So so they found new series for 1 over pi. For example, this is their new series, and if you know Mathematica, then this Mathematica, the built-in function for calculating the value of pi is Sudnovsky series. This is a very fast converging series. Okay. And in the last few years, many more formulas of Ramanujan 1 over pi were found by several authors. There are many authors. So these are some of the authors. I have not written the names of all authors, but these are some of them. So there are many papers on pi, Ramanujan type series, etc. So, and the last one is in 2020, when Chang Chu, he devised a new method to calculate to find the series for 1 over pi. And from that, he derived 4 series of Ramanujan. So that was only published in July 18, 2020. So there are many more work to be done on this series and related topics. And so I skip this. Then Professor Berndt and myself, we also systematically analyzed Ramanujan's original representation for 1 over pi and established many new results, including series for 1 over pi square. In fact, what we have did is that we derived the series in the spirit of Ramanujan. That means we have used only mathematics known to Ramanujan, not new mathematics developed after Ramanujan's date. Okay. And a survey of Ramanujan type series were written by us with Berndt and Chen, and that was published in 2009. But there are many more series here. For example, this is almost 105 citations. That means new papers were written based on this after this. Okay. Then there is, so that is Ramanujan's method. So then ASEM method, then Ramanujan's method. Then there is another method that is called BBP formulas. BBP, another new method were found, and this actually gives us what? This is the formula for BBP formula. What it gives? This gives the individual extraction of digits. That means suppose 3.14159, etc. This is the value of pi. This is the fourth position. Suppose I want to find only 4th position. That means this one. I don't want to find all 3.141. I want to find only 5. Okay. That means suppose I want to find the 100th decimal place, only 100th decimal place. Then these are the formulas. And here, because it is 16, the power is 16. So therefore, this gives what? The value of pi in binary. One can extract the binary digits, individual digits. So those are called PPP formulas. And now BPP formulas can be used to find the binary digits of pi. But unfortunately, there is no decimal BPP formula. So that is an open problem that we cannot extract the individual digits of pi. Okay. And there are many more calculations were there. And the last record is this one. So this world record of the value of pi is set only in January 29, 2020 by Timothy Mulligan. Okay. So he calculated the value of pi up to 50 trillion decimal places digits, and he used those Bohr's quadratic formula. Then for verification, he used Sudnowski's formula, etc. So Ramanujan type formulas, you can say. Okay, so that is the current record. So that's the current status of calculations of the digits of pi. Now I just end this with just giving you one mnemonics of pi. That means how to remember the digits of pi. So this is this. Sir, I send a rhyme excelling in a sacred truth and etc. So what is this? Sir means 3, then 1, 4, 1, 5, 9. These are called mnemonics. So there are many other mnemonics. For example, so just let me quickly give you. So this is Dutch mnemonics, French mnemonics, Italian mnemonics, Spanish mnemonics, etc. And there are songs on pi. So let me quickly scroll this. And there is a place of pi in Guinness Book of World Records. And what is that means what? How many digits one can remember. So there is a Guinness Book of World Records. So how to measure the memorizing power of a person. So these are the Guinness records. And let me see the last Guinness records. So this is Indian. In 1981, Rajan Mahadevan of India memorized 31,811 digits. 31,811 digits. But that was broken in 1987 by memorizing 40,000 by Japanese Hideki Tomoyori. But that was also broken in 1995 by Hiroyuki Goto of Japan, 42,195. And that was also broken by Chao Lu of China, who memorized 67,890 digits. But again, India is back in 2015. Rasbir Meena memorized 70,000 digits. He is a BTech alumni of BIT. And that was broken in October 21 in 2015 by another Indian, Suresh Kumar Sharma of Jaipur, who memorized 70,000. Okay, so that is the record. So if you want to break the record of memorizing the digits of pi, so you have to memorize these digits, 70,031 digits. And these are the first 10,000 digits. First slide, second slide, third slide, fourth, fifth, sixth, seventh. So 7 slides are required to write the 10,000 digits. So almost 49 slides will be required to memorize 70,000 digits. So one has to memorize 49 slides. And these are the Pi books: History of Pi, Pi and the AGM, then Joy of Pi. This is Biography of this world's most beautiful number. This is Pi Unleashed. This is Number Pi. This is Pi, a source book, and this is the latest Pi book, Pi, the Next Generation. Okay. So I would like to thank all the members of the organizing committee for their kind invitation. And so thank you so much. Thank you. Thank you all, and stay safe. Thank you.
Thank you, sir. Thank you, sir, for your nice deliberation. I really believe that all the participants are benefited from your lecture. Thank you once again. Next, we move on to the discussion session. We have with us Dr. Subham Sen from Tezpur University. I believe that he must involve in discussion with you. So, and Dr. Jonali Chaudhary of Cotton University.
Yes.
Let me unmute them first. Subham Sen, and I have also seen Ninal Kolita from Pandu College. I really believe they might want to have discussion with you. Hello, Subham.
Yes, Junali, I could hear you.
Hello.
Hello, Junali, could you hear me? Hello,
Jonali, yeah. I am here. I am hearing you. You are audible. And
Hello,
Jonali,
can you hear me?
Yeah, I can hear you, Shubham.
Yeah.
and Jonathan, okay. Do you want to discuss with him relating to the subject topic? Shubham?
You see, we discuss every day, but the pi is endless. So our queries, right? So I just want to say something to sir and ask something from Noandip sir.
Yes.
So in our school days, we see pi, but all occurrences of pi are in the geometry. That means when we want to find out the area or the perimeter of a circle or cone or say cylinder, etc., we
Yeah.
see pi. But in your slides, we see that pi is there everywhere in infinite series. It is there in Ramanujan mathematics. It is there.
Yes.
And sometime later, after doing MSc, I also knew that it is there in statistics as well, right?
Yes.
And integration also it is there. So how the pi actually came from geometry to these other branches or other areas of maths rather? They came gradually over time, or some mathematical discoveries were there that we are never taught.
Yeah, that I told you. That calculus was discovered, and pi was related to arctan of x. Okay, integration of 1 over 1 plus t square from 0 to x is nothing but of tan inverse of x. Okay, and once tan inverse of x, that you put x equal to say 1, you will get pi over 4. So in that way, it is connected. And so that is the thing, that it is the period of a kind, right? So that's how it came to calculus. And once it came to calculus, then it came to other things. And similarly, it is related to AGM, arithmetic geometric means. That was a very unusual application, and that Gauss found that it is AGM is connected to what is called perimeter of lemniscate. Okay, so that is very interesting. Okay. And all those are connected: elliptic integrals, then perimeter of lemniscate, and AGM and pi. So all are connected. So therefore, once those are connected, so those are connected to some modular functions. Okay, so all these new things came. And similarly, Ramanujan, he connected to what is called class invariance and modular equation. And once this modular things came, so it went to other branches of algebra and other things as well. So, and in physics and other applications, pi came because of the periodicity necessary, because it is sine and cos appears, and those are periodic, and the period of the sine theta, as you know, or sine x function, cos x function, all involves pi. Okay, so therefore in physical applications that came. And in probability, pi came because of this infinite series and other things, and so Monte Carlo method and those random numbers, all this pi came, and in binomial theorem, etc. Okay, so that is my understanding.
Okay, thank you, sir.
Okay, thank you.
Thank you, Subham. I have seen one of my friend from Cotton University, Dr. Jonali Chaudhary. Jonali?
Yes.
Jonali, unmute yourself. Jonali, do you have to ask something, Jonali? No. Then another friend I have seen, he's from physics actually, Aprotim, he's from GC College, Silchar.
Hello.
Hello.
Oh, Jonali is here. Yeah, Jonali is here.
Yeah,
Janali?
thank you for your nice presentation.
Okay, thank you, Sonali.
No question actually.
Thank you.
Okay. Thank you. Mrinal Kolita is there, no? Mrinalda, hello. Mrinal Kolita. Yeah, is it? Mrinalda. Okay, most probably there is no question. So, sir,
Hello.
we have some question in the question answer forum, huh? Question and answer forum. Should I read them?
Okay. Yeah.
For you? Yeah. There is one question from Deepu Bora. Why only pi has this value? You can see, sir. Question and answer forum.
Yeah. What does it mean? I do not know. Actually, the question.
Yeah.
Why only pi
why
has
only
this value?
pi has this value?
Similarly,
Then-
one can find the value of E, but there are very fast converging series of E already, but there are many more series of pi. So therefore, pi is more interesting. Pi appears in everywhere. So therefore, people are more interested in the value of pi. But for other irrational numbers also, millions and billions decimal places were found. And one application of this finding the value of pi up to trillions of values, trillions of decimal places is that those algorithms can be used to test the computers, supercomputers. So Canada and other people, they are actually using these algorithms, calculating the value of pi in deciding whether a newly invented computer is compatible to the others or not. Okay. So that is what. And then
So
one
another
Mayuri
question was
Soitia.
there from
Yes,
Dr.
I can see the.
Yeah.
I can see the
You have seen.
question.
Yeah, sir.
Why is so important in
Yes.
maths? That's I already told you, so you might have got the answer. Then is pi constant available in abacus calculator invented by Pascal? Yes, yes, maybe, yeah. They tried mechanical calculus. They tried.
So there's. So last one.
Last one is
Raj,
asking that pi take the values 3.14 and also 22/7. But in some areas, we can only use 22/7 for getting the answer. That is just approximation. 22/7 is a approximation of value of pi, approximate value of pi only up to 2 decimal places, 2 decimal correct places. From the third onwards, it is not correct. So it is just, and also I want to say that 22/7 is the best approximation for a single digit denominator. That means you cannot get a better approximation if it is less than 7. Okay. So the next best approximation is 306/1. The best approximation is 355/113. 355/113. So you see that between 7 and 113, there is a large gap. Okay, there is a large gap. So, and all these are connected to actually continued fractions. That I have not talked. That is a technical one. But 22/7 is not pi. 22/7 is a rational approximation, which is correct only up to 2 decimal places. That should be remembered. Okay, that should be noted. Okay. Any other question?
Next. Actually, Dr. Sobita Gupta, actually, what is the value of pi at now?
No, it is irrational. So therefore 50 trillion, up to 50 trillion has been found. That is the record.
One of my friend, Oprotim Nag, he is from GC College, Silchar. He has asked you, as you said, pi was recent in 1706. Prior to that, what was this ratio called? Okay.
That was different notations were used. For example, C was used, only C, and there are some other notations, different notations. No proper pi was used. Pi was used only for the first time in 1706. Other letters were used, C, then P, etc. Not pi, not the Greek letter pi. And Greek letter pi actually comes from periphery, or the Greek word periphery. Periphery is this perimeter. Okay, so Greek letter P is pi, so therefore it is pi.
So last question most probably from Gokul Ras. Sir, why the value is so important in the problems even though the original value is unknown?
That is very unclear. Yeah. So when the original value is unknown. The original value is unknown means it is known, but one can calculate up to that decimal places. This is irrational number, so no, you cannot calculate up to all. That is not possible. Okay. Hello. Hello.
Sir, most probably there is no question.
Okay.
Thank you, sir. Okay. Next, I request Mrs. Neha Hazarika, Assistant Professor, Department of Human Resource Management, Golaghat Commerce College, to offer the vote of thanks. Sneha, over to you, Sneha.
Thank you, Corby ma'am. Good afternoon, everyone. We have come to the end of today's session. It is my privilege to deliver the vote of thanks on this occasion on behalf of Golaghat Commerce College, its entire fraternity, and the organizing team. I take this opportunity to express my sincere thanks and gratitude to our resource person, Professor Noyandip Deka Borua Sir, Professor, Department of Mathematical Sciences, Tejpur University, for gracing this occasion virtually and sharing his knowledge and research on the topic, the story of history of pi, a mathematical constant. Thank you very much, sir, for your informative and enlightening presentation. I would also like to thank Mr. Paresh Saikya, sir, Principal, Golaghat Commerce College, for his dedication and support in organizing this webinar. Special thanks to Dr. Jibanjyoti Kakoti, sir, Coordinator, Internal Quality Assurance Cell, Golaghat Commerce College, for his encouragement and leadership to make this webinar a successful event. My heartfelt thanks goes to all the members of the technical team, Ms. Sonashri Das, Mr. Harmeet Singh, Ms. Himadri Gogoi, and Mr. Onupal Goswami for giving us an opportunity to have a discussion on this interesting topic. I further extend my heartfelt thanks to the coordinator, Dr. Korobi Devi, Assistant Professor, Department of Mathematics and Statistics, Golaghat Commerce College, without whose support it would not be possible to organize the webinar. Last but not the least, my special thanks goes to our virtual participants for being with us. So once again, thank you very much. Thank you, ma'am.
Thank you, Sneha. Finally, we are at the end of the session. It's time to say goodbye. Thank you all. Have a nice day. Thank you.
Thank you.
So, yeah.